What's that? There's hail and tornadoes coming?
Yeah.
Is that what you're saying?
Yeah.
Well, we may have a short class in the setting.
Yeah.
I was here one evening when there was a tornado out here in this direction. We spent an hour in the stairwell before.
My car in the garage.
Okay, we need to get started here. All right. Well, hopefully we'll make it in one piece without having to evacuate. All right. It does look kind of dark out there, though, doesn't it? Let's see. First of all, just a reminder that the homework number 8 that's due this coming Friday, and I am, as of right now, planning on having the test a week from Friday. I mean, that's my plan as of today. We'll see how that goes, but that's my. And so, with that in mind, I'll be working tomorrow on finishing up the practice set for the test. So we'll have that available for you guys. All right. Now, we were working on a problem here the last time, and actually I want to finish this, so we're talking here, we're talking about triple integrals, and the problem that we started out with was a triple integral over some solid E of z dv, and E is bounded by some planes, the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equal to 1. And where we had left it off the last time is we had converted this into an iterated integral, which is what you have to do in order to figure out the answer. Integrated integral, and this is what we had. We had 0 to 1 for dx, and then y going from 0 to 1 minus x, that would be dy, and then z was going from 0 to 1 minus x minus y. And then let's not forget that we are integrating this function z. So that's where we left it. And yes, thank you. It's dz. Yep. Thank you. So we're first integrating with respect to z, then y, and then finally x. All right. Now, so we work from the inside out, and so the antiderivative of z, of course, is z squared over 2. And then we look at the bounds here, z equals 0 to z equals 1 minus x minus y. The reason I want to do this problem is to show you that there's an easier way to work this than what you might perhaps do. Let's put our other integrals here, y equals 0 to 1 minus x, and then x goes from 0 to 1. Okay. So here we plug in our values. Our bottom value is 0. So the top value is, let me put it in parentheses, 1 minus x minus y squared all over 2. And then that's going to be integrated with respect to y. Y equals 0 to 1 minus x, and then x 0 to 1 dx. Now, the hard way to work this problem is to say, okay, I'm going to FOIL that whole thing out and then start on it, all right? The easier way to attack this problem is to do a U substitution. So remember here, we're integrating with respect to x, so with respect to y, sorry, so x is constant. So let's look and see what happens if we have the inside of the parentheses be our u. So let u equal 1 minus x minus y, and then get our du. Okay, well, 1 goes to 0, minus x will go to 0 because we're treating it like a constant, and all we're going to be left with is minus dy. Okay, so therefore, I'm going to replace dy with a negative du. So what I get here with this is minus u squared over 2 as my substitution. Instead of doing all the FOILing out. So therefore, let's get the antiderivative of minus u squared over 2, and that's going to be minus u to the third over 2 times 3. All right. Now let's get x and y back into the picture. U is equal to 1 minus x minus y. So we have minus parentheses 1 minus x minus y cubed all over 6. And then we're left now with, and then this is being integrated with, let's see, y is going from y equals 0 to y equals 1 minus x. And then our outer integral is 0 to 1 dx. Okay. Now, this isn't even going to be so bad when we plug in 1 minus x for the y. So what do we get here when we plug in right here 1 minus x? No, let's see. The 1s are going to go away. The x's are going to go away. Let's see here. 1, okay, so that's 1. Okay, y is equal to 1 minus x, 1 minus x minus y.
Well, once you plug in the 0, you're going to.
Wait a minute. Oh, yeah, exactly. Right. Gosh. Okay. So anyway, so plugging in the top part, I will get with it here. When we plug in the top part, we certainly do get 0. And then we have to be careful here. We've got a negative, so that's going to become a plus when I subtract. And now we plug in the 0 here for y, so I'm going to get 1 minus x raised to the third power over 6. Okay. So that's not too bad, 0 to 1 dx. And then again, we don't have to be FOILing things out. I can do another u substitution. This time let u equal 1 minus x. So du is equal to minus dx, or dx is equal to minus du. And so this becomes minus u to the third over 6. And so I get its antiderivative. That'll be minus u to the fourth over 6 times 4, or 24, which is minus 1 minus x to the fourth over 24. And that is what I'm integrating from 0 to 1. And when I plug in a 1, I get a 0 for my result. But when I plug in the 0, remember we're subtracting, so I have a plus 1 over 24 as my answer. The reason I wanted to do that is just to show that don't necessarily always be so quick to FOIL things out. Check to see if you can do a u substitution to make it a little bit less laborious getting the antiderivative. Okay. All right. right, I've got a couple more here on this section, just to get the idea of how to set these things up. They have to be set up as an iterated integral, and then you should be good to go. So here we have a second one, evaluate triple integral over some solid E of the square root of x squared plus y squared dv. And so what is the region where E is bounded by y equaling x squared plus z squared and y equaling 4. Okay. Now, it really helps to do a rough sketch of what we're talking about here. So here's our axes. All right. Now, this one here, y equals x squared plus z squared, it's going to grow along the y-axis here. When x is 0 and z is 0, it's at 0. But then as x and z get bigger, it goes out like a parabola. So it goes this way along the y-axis. Okay. Okay, that's this part of it right here. The upper part of this is a plane where y is equal to 4. So we have this, basically this cutoff right here where y is equal to 4. And so this whole solid in between there is what we're integrating over. All right. So basically, let's see here. What we have here is we have an upper y value and a lower y value. So this is what I call the upper y, and this here is going to be my lower y. All right. So we're going to set this up initially as this. Okay, first of all, we're going to do the lower y equals x squared plus z squared. Upper y is y equals 4. Let's put in what we're integrating, square root of x squared plus y squared. And this, of course, we're integrating with respect to y. Now, I'm going to do this in 2 parts here. The rest of this, then, is going to be integrated over this region D. D here is going to be in the xz plane. It's basically the, shall we say, the shadow or the projection, onto the xz plane. So basically, we see where does our lower meet our upper? Well, the lower meets the upper at x squared plus z squared equaling 4. And that's going to be our shadow. Over down here in the xz plane, we're going to have a circle here that is our D. Everybody okay with that? Now, it's always good to then just put another little diagram of your D. Now, this is in the xz plane, so let's put z as the vertical one and x as the horizontal one. And this is basically, what do we have here? It's x squared plus z squared equals 4. So this is a circle of radius 2. So we're talking about a circle radius 2. All right. Okay. Now, okay, let's then get let's just do this next here. Let's just continue with this. And let's plug in, first of all, let's plug in the and the, let's do the antiderivative. Okay, x squared plus, oh, that's right, okay. I'm sorry, guys. This right here, I knew something was wrong. Go back up to the initial function that we're integrating. It's not x squared plus y squared. It's x squared plus z squared. And let me change that right here. That's x squared plus z squared. Okay. All right. So let me get the antiderivative here. Let's do the inside one here. And we're integrating with respect to y, so therefore x and z are both going to be considered constant. So this antiderivative here is just going to be y times x squared, square root of x squared plus z squared. And here where our bounds are, the lower bound is y equals x squared plus z squared. Upper bound is y equal to 4. Okay. And then here we have dA. All right. Let's plug in the top and the bottom ones. When we plug in, so this, the only y we have is right here. So when we plug in the top, we're going to get 4. When we plug in the bottom, we're going to get x squared plus z squared. So this is what we're going to get then. 4 minus x squared minus z squared in parentheses times the, times the square root of x squared plus z squared. All right. And that's all this double integral over this region D. Okay. So we've gotten that far with it, integrating with respect to y. Look at what we have here. We've got x squared plus z squared under the radical. We've also got an x squared and a z squared inside the parentheses. The region that we're integrating over is a circle of radius 2. So what might be the easiest way to go then here as far as then calculating this double integral? Could we switch to another set of coordinates? Yeah, this really then says, okay, let's figure this out using polar coordinates. Okay, that's a good question. We just work the same way. So I'll show you this. So let's do polar coordinates. So Jenna's question was, well, how can we do polar coordinates if we have z in x as opposed to y in x? And it'll work the same way. So let me just draw this region again here. Here's our z-axis, here's our x, and we've got this circle, this is our d, and the radius here is 2. Okay. Well, normally we let x, we do the substitution, x is going to equal r cosine of theta, right, when we go to polar coordinates. Now, normally, it's y equals r sine of theta, but we don't have a y-axis here, we have a z-axis. So we're just going to let z equal r sine of theta, okay? We'll just replace it. So we're going to let z equal r sine of theta. Okay. And so therefore, x squared plus z squared is therefore going to equal r squared, all right? All right, so let's see here. So we're going to have here, we're going to integrate with, let's see, it's going to be dr d theta. What else do I need to put in there besides just dr and d theta? Yeah, it has to be r dr d theta. So that replaces the the dA gets replaced by r dr d theta. So let's integrate first with respect to r. So r is going to go from 0, the center. Now this is a radius 2, so it's going to go to 2. And what are we integrating? We're integrating 4 minus r squared in parentheses, and then the square root of x squared plus z squared is just r. So we have 4 minus r squared times r dr d theta. And then we also have to look at the theta. The theta goes from 0 to 2 pi. Okay. All right. So this is just all r stuff. One thing you can do right away here is separate these out into two single integrals. This can be, we can just separate here 0 to 2 pi of d theta as one single integral, and then the other one from r equals 0 to 2 of, what do we have here? R squared times 4 minus r squared dr. All right, like that. Okay, that's one thing we can do. So now we just have two single integrals to do, and so let's do the r one here. So this is 4r squared minus r to the 4th power. So get the antiderivative, that's going to be 4r to the 3 over 3 minus r to the 5 over 5. And we're integrating from 0 to 2. The other one is just going to be theta from 0 to 2 pi. And of course, that's just going to be 2 pi. So we have 2 pi for the first integral, and then here, let's see, 0 down below, so those will just 0 out. So this will be 4 times 2 to the 3rd, which is 8 over 3, minus 2 to the 5th, 32 over 5, like that. So it's 2 pi, 32 over 3 minus 32 over 5, and that's going to give us, when we combine these, we're going to get 64 over 15 times 2 pi, or 128 pi over 15. That's our answer. So you want to be alert for when we can benefit from polar coordinates. This would have become a much more hairy problem if we had kept it strictly in terms of x and y. All right, but because we had a circle here for our d, and because our function was set up basically to use polar coordinates, you want to do that, make it easier. The whole key with these triple integrals is getting it set up as that iterated integral initially. What is iterated means something like this: outer integral from a to b. Then we have one from, say, maybe a function something to something, and then we have our inside from something to something. Okay, we have the limits of integration. That's an iterated integral. Yeah. All right. Then I think this is the last one for this section. No, there's actually two more. All right. And with this next one, we're asked to find a volume. Find a volume. Oh boy, it really looks dark. It really looks dark out there. Yikes, I don't like that. Of a solid that we'll call E. And this solid, we're given bounds. It's bounded by, let's see, x goes from 0 to 3. Y goes from 0 to x. Z goes from x plus y. And then, from x minus y to x plus y. Now, before we actually do the problem, I want to give you this fact or a reminder here about this. The volume is going to be that triple integral over the whatever our solid is of 1 times dV. Okay, that's the formula for a volume. So I'm going to put asterisk by that. Just remember also we had the from previous, we had that the area is the double integral over a two-dimensional region of 1 times dA. That's another thing that we had previously. So these are both related to each other. So we're going to use this formula here for obtaining the volume. Okay. Now, this problem is actually a pretty nice one because we actually are given the bounds of integration here. We're given that x goes from 0 to 3, y goes from 0 to x, z goes from x minus y to x plus y. So we're basically handed the iterated integral on a platter, all right? Now with this in mind, which variable am I going to integrate first? Which am I going to then integrate second? And which will be my last one? Okay. Okay. Right, exactly. So Jenna says do z first because we have two variables here for z. Then do y because we have a single variable there. Our outside limit is always going to be just numbers. So this is how we're going to set it up then. X is going to go from 0 to 3. Y is going to go from 0 to x. Z is going to go from x minus y to x plus y, 1. And then we do dz first, dy, and then dx. So that's set up for us. Okay. All right, so let's see here. Let's start with the middle, the inside one, and that the antiderivative of 1 with respect to z is going to be z, and we're integrating that from z being x minus y to z equals x plus y. And then let's put our outer bounds here. Y goes from 0 to x goes from 0 to 3. All right. Wait a minute, it's for the volume? Is that your question? Yeah, if they're asking you for the volume, it's going to be this formula here. You've got the triple integral, and your function inside is just a 1. Okay. Similarly for area, you're going to have a double integral, because it's only 2 dimensions, but you're also just going to have a 1 in there. Okay. All right, so let's see. This is x plus, what is this? X plus y minus x minus y. So I think that comes out to be 2 times y. All right. So what we have is 0 to x, 2y dy, 0 to 3 dx. Okay. So we do the antiderivative of 2y, and we get y squared, and that's going from 0 to x. And then our x is 0 to 3. This is actually a pretty short triple integral problem. Okay, let's put in our limits here. The top one is y equals x, so that's going to be x squared. The bottom one is 0, so that won't put down. So we have 0 to 3 x squared dx. And let's get the antiderivative, x to the 3 over 3, going from 0 to 3. And so what we come up with is 27 over 3, and our answer then is 9. So that's the volume. Okay. Last one here with this section is this. evaluate triple integral over e of 6xy dv, where e lies under the plane z equaling 1 plus x plus y, and it lies above the region in the xy plane bounded by y equals the square root of x, y equals 0, and x equal to 1. Okay. Now, first of all, we know we have to make this into an iterated integral. Okay, we're given an expression for z. Z lies under z equals 1 plus x plus y, and it lies above a region in the xy plane. Now, on the xy plane, all the values of z equals 0. So therefore, what we have here is we have our large z, or larger z, is 1 plus x plus y, and our smaller z is equal to 0. So we're integrating between those two areas. In fact, here's just a little diagram of what we're talking about, x, y, and z. Okay, we're bounded below on the xy plane. This plane here, z equals 1 plus x plus y. Well, when x and y are 0, then z is equal to the value 1. And then as x and y get bigger, z gets bigger in value. So this thing then comes out, goes up like this, and goes up like this, keeps getting bigger in value. We're integrating over an area here in this area over here in the xy plane, but let's draw a diagram here of what we're integrating over. Okay. What you're going to see, let me tell you this, what you're going to see on the test, which I'm also in the process of making up, is that for a lot of the problems, I'm going to just give you, you're going to see a blank cross there with some squares inside there, because for a lot of these problems, you need to figure out that region D in 2 dimensions. And so you'll use that to help sketch out your region D, all right? And that's also a reminder for me to give you that you need to sketch that out. So our region on the xy plane, what are we told here? It's bounded by y equals the square root of x, y equals 0, and x equals 1. So here's y is equal to 0, and let's see, x equals, and then y equals the square root of x. That comes out like this. Okay. And then x equal to 1 is right here. So this right here is what we are integrating over in the xy plane. So let's set up this integrated integral. So first of all, we're going to have z going from 0 to 1 plus x plus y. Let's put our function here at 6xy, and that's dz. Now let's set up our integrals with respect to y and x. Anybody want to give me what they might want to integrate over first, and what the bounds would be? Okay, so in other words, going up this way with an arrow going up. where y goes from 0 to the square root of x. Okay, so let's do that. So that's our middle one here, y equals 0 to y equals the square root of x, so that's our dy. And then what's our bounds for x? 0 to 1. And that's our dx. So that's half the battle of setting up the integral there. All right. And let's see, let's just, wow. What's that now? You don't want to go outside. No, I don't want to go outside either. Oh, did you have a question? Yeah. Well, you're running into a possibility of error if you don't do some kind of sketch. Let's put it that way. But if you set it up correctly, that's fine with me. All right. But I'm encouraging you to sketch something so that you don't make a mistake. Okay. You guys are probably on the inside. You guys probably don't realize do you realize how it's raining outside? It's just, I'm like talking over this deluge out there. All right, let's do this thing here. Start with the inside integral, which is with respect to z. Well, x and y are constant, so my antiderivative here is 6 times xy times z. All right? And then that gets integrated from 0 to 1 plus x plus y. And then I have my two outer integrals. Okay. So we plug in the top one for z, so we have 6xy times 1 plus x plus y, and then we subtract 0. All right. Now with this one, I am going to have to just distribute this. So this is what? 6xy plus 6x squared y plus 6xy squared. All right. All right, so we need to then, so we're integrating this next one with respect to y, where y goes from 0 to square root of x, and then x goes from 0 to 1. So our next one is integrating this with respect to y, so x is constant. So what do we have here? I think the first one's going to be, what, 3xy squared plus 3x squared y squared plus 6xy to the third over 3, which is 2xy to the third. All right. Okay, and then that gets integrated from what? Y equals 0 to the square root of x. And then our outer one is 0 to 1 dx. All right. Okay, well, plug in the square root of x here, and y squared, the square of the square root is just x. So this first one becomes 3x squared when I plug that in. This one becomes 3x squared times x, so that's 3x to the third. This one, y to the third becomes basically x times the square root of x, and this is 2x times x times the square root of x. And so this is really what? X times x times x to the 1/2 power. So that's x to the 5/2 power, 2.5. So I'm basically integrating, so basically what I have here then is I'm integrating 2x to the 5/2 power. So that's going to give me 2x to the, what, 7/2 power divided by 7/2 or multiplied by 2/7. And then this we're going to integrate from 0 to 1. All right. Everybody all right with that? The last term here is 2 times 2 over 7 times x to the 7/2. Basically, I've simplified what I'm doing the antiderivative of it, and I'm getting the antiderivative of 2x to the 5/2 power. So that gives me this right here.
I think you got the antiderivative of the x squared up here.
How did I obtain these? Okay, no, I haven't done those antiderivatives yet. All I'm doing here is basically plugging in the square root of x.
But you got the antiderivative of the last term.
Oh, you're right. You're right. I'm getting ahead of myself. Right. Thanks. Yep. 2x to the 5/2 power. All right, let me write this again. 3x squared plus 3x to the 3rd plus 2x to the 5/2 power, and getting that from 0 to 1 dx. All right. Thanks. So 3x squared becomes x to the 3rd. 3x to the 3rd becomes 3x to the 4th over 4. 2x to the 5/2 becomes what I had up there, which is going to be 4 over 7 x to the 7/2. And then that's from 0 to 1. All right. Okay, so that's just going to be 1 plus 3/4 plus 4/7 minus 0. And when we combine, that becomes 65 over 28. Okay, with common denominator. All right. Okay, so as we see here, there's plenty of opportunity if you're not really focusing carefully to make arithmetic mistakes or to get ahead of yourself and to mix apples and oranges. So you do have to be careful with these. Why don't we take a 5-minute break, and then we'll see what I would like. Then I think we can make it through these cylindrical coordinates afterwards. Oh, sure. Jerry, is that what you're talking about? Okay. Oh, what's this? I will tell you guys this, at Eureka and Lafayette, it wouldn't surprise me if at any moment they have us go to the stairwell. So if everybody here, if I suddenly disappear, it's because of the weather situation.
Number 12. That one, that's it, that's right.
Ooh. Okay, here we have it. It's right there. Okay, cosine, cosine R, d theta, d is the disk, the center at origin, radius. Yeah, so it's the whole disk from 0 to 2 pi. Yeah, that's it.
Okay. So
Right.
integrate
So
that.
this you're going to need to use integration by part.
Okay, so how about
Right, but otherwise you've set it up.
Okay. Thank you.
Office of Emergency Management has issued a severe thunderstorm warning for St. Louis County through 11:30 a.m.
I know what the warning, I know what the siren sounds like here when we have to go to the stairwell, because I've been through that. So. Hopefully it's not the lull before for what gets worse. Let's just. All right. Okay. Let's go on to the next section here, which still involves the triple integral, except except we are going to be going to a different coordinate system because it'll make life easier for ourselves because of the kind of problem we have. So this is section 15.8, And this is triple integrals using cylindrical coordinates. Triple integrals using cylindrical coordinates. All right. Okay. Now, what basically these cylindrical coordinates are is they're taking the polar coordinates and moving it into 3 dimensions. So now we move polar coordinates, because remember, polar coordinates are 2-dimensional. We're moving them into 3 dimensions, okay, with the use of the cylindrical coordinates. So we've got 3 variables here that determine a point. So a point, we'll call a capital P, in 3D space can be given by r theta. These are from the polar coordinates, but our last coordinate is z. So this is how it's represented in 3 dimensions. Here's our x and our y and our z. So we have a point up here. Basically, if we drop a perpendicular line down, we get a point in the xy plane. So this is our point P. And this then is the z, which is just the z coordinate. Now here it drops down to the xy plane. So with the xy plane, we can then represent that point there in terms of polar coordinates, where we have r, that's the distance to the origin, and we have theta, which is the angle with the positive x-axis. So between those 3, we have the point in terms of, and we do it in this order, r, theta, and then z. And so that will determine that. Okay, so r and theta are the same as the polar coordinates. So let's just review here what the relationships that we have with rectangular. R squared is equal to x squared plus y squared. X is equal to r cosine of theta. Y is r sine of theta. And finally, the tangent of theta is y over x. So those are the same relationships that we had seen previously. Now, z is the same as the z coordinate in the rectangular system. Z is the same. Okay, it's just the distance from the xy plane. All right. Using this system can be helpful if we are doing problems involving cylinders. This coordinate system is good if we're doing problems involving cylinders or anything that's symmetric about the z-axis, or a solid that is symmetric about the z-axis. Okay. So first of all, I just want to show what a couple of different shapes look like in terms of these cylindrical coordinates. How about, let's say we have a cylinder centered around the z-axis with a radius equal to c, with radius c. So this would be something like this, xyz, cylinder around the z-axis, radius of c goes up and down, like that. Okay. Now, in terms of rectangular coordinates, this is represented as x squared plus y squared equals c squared. C goes all the way up and down, so we don't have c in there. Now, this can be represented in terms of the cylindrical coordinate by replacing x squared plus y squared with r squared. So it can be represented as r squared equal to c squared. And then if I take the square root of both sides, we can represent it as r equals c. So this is its equation in cylindrical coordinates. So it's any point that has a distance of c from the z-axis. So it just goes all the way up and down. And because it's so simple like this, for a cylinder, that's why these are called cylindrical coordinates. We can look at another surface. Let's ask this question. What type of surface is given by z equaling r in cylindrical coordinates? Well, one way to find out this is just to get it in terms of rectangular coordinates and see what we've got. Remember that r is equal to the square root of x squared plus y squared. So this equation here is z equals the square root of x squared plus y squared in rectangular coordinates. And if I square both sides, I end up with z squared equals x squared plus y squared in rectangular. And that's a cone. So let's look at what that looks like, a cone. So when x and y are 0, z is 0, so we have a point right here. As x and y get bigger, z gets bigger. So it goes out like this, upwardly, and then it also goes below the xy axis. It also goes down like this. So it's a cone. That's the answer. And just by getting it in rectangular coordinates, we can see that. Okay. So what we want to look at next then is actually doing some triple integrals with these coordinates. Now, so triple integral. Okay, let's define, let's get a solid. Let E be the solid given by the following. All right. Z goes between, Z is less than a function of x and y, U2, let's call it U2, and bigger than another function of x, y, call it U1. R is less than a function H2 of theta and bigger than a function H1 of theta, and I'll show you in a diagram in just a second. And theta say, goes from, is bigger than alpha and less than beta. So these are the bounds here of this solid in cylindrical coordinates, z, r, and theta. This is what it looks like. Okay. So z here, this is our lower function for z. This is our upper function for z. So z ranges here. And then when we project this down onto the xy plane, its shadow is this region here called D, where notice it is ranging in polar coordinates from a lower function of theta, as theta changes, r changes, to a higher function of theta. So r goes out that way. And then theta, we have a wedge here. Theta is going from alpha to beta, like that, on our shadow of our region. So that's what this looks like. When we set this up then, we're going to want to set this up in cylindrical coordinates. So here's our iterated integral. Okay, we're going to start with the z. We put our function in terms of the cylindrical coordinates, and we're going to do a couple problems with this. Notice, because it's involving polar coordinates, we have r, dr, d theta. So we have that extra r hanging around. Then we integrate our r between the two functions. And finally, we integrate our theta between the two values. So again, we can theoretically have here a function of, on the inside integral, a function of two variables. On the one next to it, a function of one variable. And on the outside, we always just have numbers, right? This little wedge here just shows the little wedge that we integrate, and its dimensions are dz and dr and r d theta, which gives us r dz dr d theta. So again, big thing, don't forget the extra r there. All right, so let's do an example of this. And so we want to evaluate the following. Integral from -2 to 2 of minus the square root of 4 minus x squared up to plus the square root of 4 minus x squared. Inside one is the square root of x squared plus y squared, and the upper one is 2. The function that we're integrating is x squared plus y squared, and here are our rectangular coordinates here. So we're integrating z between, oh yeah, thank you, gosh darn. Z from square root of x squared plus y squared to 2. Y goes from minus, that's radical to positive. X is going from -2 to 2. So actually, before we convert this into cylindrical coordinates, let's get an idea of what this thing looks like. All right. So here, z is equal to x squared plus y squared. No, sorry. Z goes from the lower function of z is, so the lower z is equal to the square root of x squared plus y squared. And the upper z is z equaling 2. All right. Well, the square root of x squared plus y squared, this is the same. If I square both sides, this is a cone. Z squared is equal to x squared plus y squared. So on the bottom part, the bottom lower z is going to be a cone. My upper z, though, I stop this at z equaling 2. So this whole region here is what I am integrating over. Now, we have to look here at my projections down here, because this is going to be projected onto the xy plane when I go down here as a circle. Okay? Now, in the xy plane, what do we have here? We're told that the upper y is y equals, so the upper y is 4 minus x squared, and the lower y is minus 4 minus x squared. Well, actually, what this means is if I square both sides, y squared is equal to 4 minus x squared, or x squared plus y squared is equal to 4. So my upper y is this upper half circle. My lower y is the negative of that. It's the lower half circle. And then my x goes from minus 2 to plus 2. All right. All right, and what we're integrating from then is from the lower y to the upper y, so the arrow goes up like that. All right, this is just a sketch of what we're integrating over. This really is, to speak to Jenna's question, this is really a case where I didn't necessarily have to be drawing all this stuff in order to evaluate this, all right? But it can be helpful. So let's put this thing in cylindrical coordinates, and we're going to have a lot easier problem here. Okay, so convert to cylindrical. All right. Now, first of all, the function that we're integrating is x squared plus y squared. So that's the same as r squared. Now, z is going from the square root of x squared plus y squared to 2. Well, what will I replace for this lower bounds of integration for z? What am I going to write there instead of the square root of x squared plus y squared? Well, what's in cylindrical coordinates, x squared plus y squared is equal to r squared. So if I'm doing the square root of both sides, the square root of x squared plus y squared just equals r. So that's my lower bound for z. Z equaling r is my lower bound. My upper bound is still the number 2. And this is my dz. Okay. Are we okay with that so far? We're just trying to get everything in terms of cylindrical. So notice here I'm writing my function, in terms of cylindrical. In terms of cylindrical coordinates. Okay, that's my innermost one. Let's go beyond that. Now here, well, actually, I take back what I just said. I think at the very least, you should draw this in order to get your r and d theta. So this projection onto the xy, you definitely should draw. And to help you. So let's look at what we're integrating here over on the XY plane. I've got a circle, its radius is 2, and it goes all the way around, it's a circle. So what would be my R? So we have R and theta as my two other variables. So what would be my limits for the R? 0, it starts at 0, it goes out to the 2. That's my R. And then remember, we're going to have here, we're going to have R d theta. So don't forget this extra R here. And then for my theta, I'm going all the way around the circle, 0 to 2 pi. So let's write this again. 0 to 2 pi, that's for theta. R is 0 to 2. Z is going from R to 2. Now, my function was R squared, but I do not want to forget that I have that R d theta, so I don't want to omit that R. So right away, I'm going to multiply my R squared by that R, so I'm integrating R to the third power. And then we have dz, dr, and d theta. So it's now set up. Okay. All right. Okay. So basically we go from the inside out. The inside is with respect to z, so R and theta are constant. Okay. All right. So my inside antiderivative is going to be R to the third times z, as z goes from R to 2. And then I have 0 to 2, 0 to 2 pi, dr, d theta. And let's plug in the values here. We get 2 times r to the third minus r times r to the third, so that's r to the fourth. So that is what I'm going to integrate now with respect to r from 0 to 2, and then theta from 0 to 2 pi. Now, certainly right here, you could separate this out as the following. 0 to 2 pi of d theta times 0 to 2 of 2r to the third minus r to the fourth dr. Just separate it out and figure out your two your two definite intervals. Okay? All right. So the first one is going to become 2 pi when we get that antiderivative. The second one, we get our antiderivative, is going to be 2r to the fourth over 4, so that's going to be r to the fourth over 2 minus r to the 5 over 5, and then that's going to be from 0 to 2. Right. All right, so that's 2 to the fourth, which is 16 over 2, that's going to be 8. 2 to the fifth is 32 over 5. The bottom ones are 0. So I think this is 40 minus 32. That's going to be, what, 8 over 5, right? Yeah. 8 over 5 times 2 pi. So we have 16 pi over 5 as our answer here with this. All right. So definitely, in order to make sure you get the bounds of integration right, you should, 99% of the time, you should draw that region in D, with either the XY plane or whatever, XZ plane, whatever plane it is, so that you get your bounds of integration correct. Okay. Now with this, I just have one other problem for this section, and The only thing this section does is it just kind of transforms polar into 3 dimensions, so it's really only a couple of problems I really need to go over. Here's the second example. The solid that we call E lies within the cylinder. X squared plus y squared equals 1. All right. Below the plane z equaling 4, and above what's a paraboloid. Remember all those different surfaces that we had towards the end of last semester. Paraboloid, z equaling 1 minus x squared minus y squared. Z equals 4, yes. All right. This also, we have some other information here about the density. So this is going to tie in with that one application that we had. The density at any given point is proportional to the point distance from the z-axis, or the axis of the cylinder. And finally, what are we asked to find? We're asked to find the mass of this solid, E. All right. First of all, let's kind of review what we're talking about here. We're not just asked to find the volume of this solid, we're asked to find like how heavy it is, the mass. So this is the formula for the mass. Mass, in this case, is equal to a triple integral of a density formula. Let's just have it as a density of x, y, and z, dV. So we have some kind of density formula that we integrate over the volume of the mass. This is basically the fact that mass is equal to density times volume. That's where that gets derived from. Okay, so this is what, in general terms, what we're going to be using. Now, first of all, I think we need to figure out what's our formula for this density. We're told that the density at any given point is proportional to its distance from the z-axis. So when we say two things are proportional to each other, we mean that one is some constant times the other one. As the other one gets bigger, the one gets bigger, and the other gets bigger. Okay, they're directly proportional to each other. But how do we represent the distance? And this is just, for right now, we're just talking about rectangular. Let's just look at rectangular coordinates. How do I represent the distance of any point from the z-axis? Okay, we're just going to draw a perpendicular line over to the z-axis, And how can I represent? So this point is given as x, y, and z. What would be the length of that line between that point and the z-axis? It would be r, but let's put it in terms, right now, let's keep it in terms of rectangular coordinates. It would be r. Yeah, the square root of x squared plus y squared, Pythagorean theorem. So basically our density then, we have that this is the distance to the z-axis, the square root of x squared plus y squared. That's the distance to the z-axis. But remember, it's proportional. That doesn't mean it's exactly equal to that. It's some constant times that. So let's just put it as a constant k. Some constant. And that's going to be our density from what we're given. Okay. So let's see what we're going to try to set up here. I think we also need to look at, before we start, let's look at a picture of what we're integrating over. And so we said it was within the cylinder x squared plus y squared equals 1. So this cylinder here, this is x squared plus y squared equals 1. And it goes all up and down the z-axis. So it's within that cylinder. We're also told that it's below the plane z equals 4. So right here, this is where z is, so it gets cut off right there at z equals 4 at the top. And then we're told it's above the paraboloid 1 minus x squared minus y squared. Well, right here, this is 1 minus x squared minus y squared. It basically, when x and y are 0, it's 1. So it goes down, down, down like this. Okay. So what we are integrating over is between here and here. Like this. Okay? So we have our upper z. Our upper z is z equals 4. Our lower z is z equals 1 minus x squared minus y squared. All right? So let's start to put this as an iterated integral here. Okay, and then we're going to switch to cylindrical coordinates. But, all right, so first of all, we're going to integrate with respect to z. Our lower z equals 1 minus x squared minus y squared. Our upper z is z equals 4. Now, the function that we're integrating is that density function, which is k times the square root of x squared plus y squared. All right? And so this first one is dz. No, not at all. No. That's the formula for this density of this thing. All right. You can, if you, I think the homework due for Friday has maybe something where you've got a different density function. So something, however it's made, will have different densities. There's no uniform density function. Okay, so what else do we have here? We then have to project this down onto the xy plane. So this is our D right here, projected down onto the xy plane. All right. So strictly in terms of rectangular coordinates, so let's look at what that looks like here. Let's look at our D. Now, this is going to be where 1 minus x squared minus y squared, where that's equal to 0, where that hits the xy plane. which is the same, of course, as x squared plus y squared equals 1. So that's going to be a circle of radius 1. This is our D right here. So let's go back up here once we've drawn this. So just again, staying just with rectangular, our y then goes from, here's the negative square root of 1 minus x squared. That's our lower value for y. Our upper value is y equals 1 square root of 1 minus x squared. And that's our dy. And then our x, so we're going to be integrating up, we'd integrate up like this. This is strictly rectangular. And our x will go from, minus 1 to 1. Oops. X equals minus 1 to 1. Now, of course, this is not the way we're going to be integrating this. I just wrote this out to show what this looks like if we were going to integrate with respect to rectangular coordinates. This is the hard, very hard way to do this. What we're going to do is we're going to convert to cylindrical coordinates. All right. So let's see here. What's my density function going to be in terms of cylindrical coordinates? It's k, some number k, times the square root of x squared plus y squared. K times r is what that's going to be. So k times r, that's my density function. And remember, we're integrating with respect to dz, r, dr, d theta. I just want to put that r right out here. And so we really have kr squared dz, dr, d theta. All right? So don't forget that extra r. So what are our limits then on z? Here we had, the lower limit was 1 minus x squared minus y squared. How can I represent that with cylindrical? Yeah, 1 minus r squared. So z equals 1 minus r squared is our lower limit, and our top limit is still going to be the number 4. All right. Now, let's look, so that's our z taken care of. Now let's look at our r. Well, we're integrating over a circle of radius 1, so r is going to go from 0 to 1. Circle of radius 1. Right? Okay. And then finally we need to do our theta, and our theta is going to go all the way around from 0 to 2 pi. So right here, right there is our integral that we now need to evaluate. So again, you've got to get an idea here of this area over the xy plane that we're integrating over. So you've got to see where that lower z actually hits the xy plane, and that's going to be basically when it equals 0. So without knowing that, we'd have no idea of what our two other bounds of integration would be unless we knew that we're integrating over a circle. Okay. All right. So finally, now that's all the hard part. The rest of it is easy. I mean, now it's just a mechanical integration here. And in fact, let's see. If we look at this, I'm actually going to just, no, I can't do that. Okay. All right, let's start on the inside. KR squared. So on the inside, let's see, on the inside, R and theta are constants. So that's going to be KR squared times Z. And that's going to be evaluated from Z equals 1 minus R squared to Z equaling 4. Right? And then we have R going from 0 to 1 and theta going from 0 to 2 pi. Okay. All right, so let's plug in the upper and lower limits for Z. Upper limit is 4, so we have 4KR squared minus, and the lower limit is minus KR squared times the lower limit, which is 1 minus R squared. So there's a little bit of algebra you got to watch out for here with this one. And so let's simplify this. This is going to be what? 4KR squared minus 1KR squared. Double minus is a plus KR to the 4th power, right? So we have 4 minus 1, 3KR squared plus KR to the 4th. All right. So that is what we then have to put here. We're going to integrate that with respect to R from 0 to 1 and theta from 0 to 2 pi. All right. Again, I can separate this out as 0 to 2 pi d theta, and then 0 to 1, 3KR squared plus KR to the 4th dr. I don't have to do that, but I don't know, I'm going to. So we get the antiderivative now with respect to R, so that's going to be R to the 3rd over 3. So the first one's going to be KR to the 3rd, and then this is going to be plus KR to the 5 over 5, and then that's going to go from 0 to 1. This first one, theta from 0 to 2 pi, is of course just going to be 2 pi. So it's 2 pi times what? Plug in the 1, I get K plus K over 5, and then subtract 0. So it's 2 pi. K plus K over 5 is 6/5 K, and so that equals 6 times 2, 12 pi over 5 times K. So notice we had to keep that proportionality constant throughout the whole thing. Of course, I could have drawn that thing out a couple steps ahead because it just sticks around as you keep integrating. But I like to do things the hard way. Okay. I hope you just have an idea of how to do these. I can't emphasize enough drawing a picture so that you accurately get the bounds of integration, and then convert them all using the formulas to R's and thetas, and then work it out. So basically what we have left here is 2 more sections. The next section is another set of coordinates that are called spherical coordinates. Those are going to be helpful for when we integrate over cones and spheres. They can be a little bit tricky, so we'll be doing that on Friday. The very last section then has to do with a Jacobian change of variables, and that can also be extremely tricky. I'm going to give you a homework problem with that. as homework. Right now, I'm thinking that as far as the test is concerned, I'm going to limit what I'm going to test on that last section. All right. But I do want to go over an example with the Jacobian. Even reading the text, if any of you actually, and I know there's a few of you that actually do look at the textbook, that last section, especially like the first 3 pages of the last section, is pretty dense reading. It's very difficult actually to follow what they're doing. And I found that tricky to follow what they were doing, for whatever that's worth. Anyway, the plan is to try for a test a week from Friday, and I'll have that practice for you, and that's it then.
Oh, is this the last one? Yeah. I've got multiple reasons why.
And I don't want to hear any of them.
The one's, I was going to do
The one's pretty good.
and I took 5-hour energy after work and everything. When I got home, right when I get started, we called power. We didn't get power until about 1:30.
Oh, so you had 5-hour energy.
So I laid there trying to go to sleep.
The house didn't have 5-hour energy. That's no good.
I don't know.
All right, I'll have this for you back Friday then.